All right, so hi everyone. Welcome to this week's South American Geometry webinar. As usual, if you wish to receive the announcements for the seminar, which runs every fortnight, then you can join our WhatsApp group, which is strictly for announcements. You can follow any of the other instructions available under the fixed info in the chat, which means texting the word, sending the word webinar to our email. You can also subscribe to our calendar for upcoming talks directly to our Google Agenda. There's a link to do that, as well as follow our pre-recorded talks in the YouTube channel. If you're here for the first time, then feel free to check the information on the chat and stay connected. So today, well, by the way, this seminar is organized by Paolo Piccione, Adrian Andrada, and myself. And today we have another Piccione on the block. It's going to be Pietro Piccione. He'll be telling us about a non-Archimedean approach to the Yao-Tian Donaldson conjecture. Before we start, Pietro, just give me a second. So Hayusun is asking whether what's been happening to the YouTube channel videos. All the recordings will be uploaded for the past period, but we might be a little late with that. Thank you for letting me know. I wasn't aware. I'll make sure they're uploaded over the next week or two. All right. So thank you, Sun, for the reminder. Yeah. So without further ado, Pietro, the floor is yours. Let's try and make it 45 minutes, if that's okay.
Sure. Thank you very much. Thank you very much, and thank you for the presentation and for inviting me to give a talk here. Yeah, so today I'll tell you a little bit of what I've been doing in my PhD. Yeah, so this has to do with this Yao-Tian Donaldson conjecture in Kähler Geometry. Okay. So what's the setting for today? So X omega for us will be a compact scalar manifold. Okay, and so omega, it's our Kähler form, and to remind you all, Kähler forms are always closed, which imply that they define a cohomology class in second degree. Okay, that for the rest of the talk I'll call alpha. So one natural question that one can ask is the following. So we started with our Kähler metric. We defined it a cohomology class, alpha. Are there other Kähler forms in the same cohomology class? It's one natural question. And the answer turns out to be yes. There are lots of them. So actually, by some Kähler magic, we know that any other Kähler form that lies in the same cohomology class actually differs to the original one by the complex Hessian of a smooth function, okay, for a smooth. But then, of course, we need to ask for this to be a Kähler form, then the sum must be positive. So what's actually we're saying is that the set of smooth function such that their complex Hessian plus our original Kähler form gives positive, this parametrizes the set of Kähler forms inside alpha, okay, by constants. And I told you that there are many of them, many Kähler forms in the same cohomology class. How come? Well, the point is that the set of potentials, so you always say it's a potential of the Kähler form omega plus complex Hessian of U. So the set of potentials, it's actually an open subset of infinity. So the span, the linear span, of this set is also infinity. So what this is telling us is that there are plenty of Kähler forms inside the same cohomology class. Okay. So if this is the case, then the possible next question is if there is any canonical Kähler form in alpha. Okay. So so canonical for differential geometry usually means some metric with constant with some curvature condition, and for us this will be constant scalar curvature Kähler metrics. Okay, so this for the rest of the talk I'll denote by CK. Okay, so then the question is there always a constant scalar curvature metric inside a cohomology class? And the answer turns out to be no. Okay, so there isn't always. But the Donaldson conjecture, which is what I'm going to tell you about today, exactly tries to predict when is there one. So the conjecture says that there exists a unique constant scalar curvature metric inside the cohomology class if and only if X alpha is said to be uniformly, and here this is not super relevant, has to do with this unicity, but the important word here is K-stable. Okay. So what is this? Well, maybe let me just tell you something. This is K-stability is a notion from algebraic geometry, so is an algebro-geometric notion. And the basic idea of this conjecture is to say that there exists a solution for some analytical problem, from differential geometric problem, if and only if something about the algebra of X in this cohomology class. Okay. So this is the conjecture. What do we know about this conjecture? Okay. So in this generality, one of the implications is already proven, meaning that if you have a CSCK metric, constant scalar curvature metric, then you can prove that X alpha is K-stable. And in this generality, this was done by Sjöström-Nerfeldt and Dervin Ross. And the other implication, that's completely open. Yeah, I mean, it's at least open. So the main theorem of today, and what I'll try to explain to you today, is the following theorem. So if you say if you assume that X alpha is K hat stable, then there exists a unique CSCK metric in alpha. Okay, so everything is a bit mysterious because I didn't tell you what's K stability, and now I didn't tell you what's K bar stability. Okay, so the important thing here is that this K bar stability is also an algebro-geometric. Is also an algebro-geometric notion, and it implies K stability. Okay, and a bit of the goal today is explain what's K stability, what's K bar stability, K hat stability, and see what exactly are the differences. Okay, and to prove this theorem, what I use and develop is this non-Archimedean approach that was in the title. Okay, so just to tell you a little bit of what was known before this theorem. This theorem was known whenever you assume that alpha had rational coefficients. So this means that alpha was actually the first rank class of some ample line bundle on the Kähler metric. This in particular would imply if you can find a Kähler class with rational coefficients, or if you can find an ample line bundle, this in particular implies that X is projective, meaning X is a submanifold of projective space. But it turns out that there are many Kähler manifolds that are not. There's this theorem by Voisin that says that there exist compact Kähler manifolds that don't even have the homotopy type of a submanifold of projective space. So it's not really something you can assume in all generality. And Chile, in this result, he also used this non-Archimedean approach that was developed by Berman, Brooks, and Johnson to solve the conjecture whenever X is Fano. So and alpha is the first class of the tangent bundle of X. Recently, Brooks and Johnson announced that actually K-bar stability is equivalent for existence of constant scalar curvature geometrics, again in this algebraic setting, so in this setting when alpha has rational coefficients. So is there any question up until now? So just to go everything we said. So we started with a complex, with a Kähler manifold, and we said that the Kähler class defined, the Kähler metric defined, the Kähler form defined a cohomology class, and natural question is to study other Kähler forms that lie in the same cohomology class. And we can parameterize a set of Kähler forms in the same cohomology class by some functions, and just by taking the complex Hessian. And the question is if we can find a Kähler form in the same cohomology class that has constant scalar curvature. And now what I'm saying is that this conjecture says that whenever you have this algebraic notion of stability, then this is enough to guarantee. Okay. Is there any question? I don't see the chat, so if you guys have any questions, please just.
On that note, if you're new to Google Meet, then there's a little hand at the bottom corner of your screen. So if you want to ask Pietro a question, you can just click that little hand, and Pietro's going to hear a beep. So, all right, so Pietro, so if you don't hear a beep, it's all right. Also, if Pietro is particularly funny or clever, you can, or thought-provoking, you can use the other things to communicate that. And that's it.
Perfect. Yep, thanks. Okay, so if no questions, we can talk about this constant scalar curvature matrix for a while. So constant scalar curvature matrix inside the cohomology class are a fourth order PDE on the set of potentials. Okay, how come? So curvature, as usual, it's a second order differential operator, and then here, since we're looking for matrix inside the cohomology class of alpha, then we know that we need to take a complex Hessian here. So if you add this up, this gives you a fourth order highly nonlinear elliptic PDE. We call this constant scalar curvature equation, the CSCK equation. But it turns out that we're very lucky because this equation has a variation interpretation, okay? Because no one knows how to solve hard equations like this, but whenever there's a variation interpretation, that makes things easier, and we're that lucky. So what does this mean? It means that there exists a functional, so a functional M that takes Kähler form and gives us real number, so actually a potential, and give us a real number, whose critical points exactly correspond to the solutions of this equation. Okay, so just to give you an idea of what is this functional, well, it's something complicated. So it's here I wrote just so you have something to keep in mind. I mean, I don't want to go through every detail, but this functional is what we call it the Mabuchi functional. Maybe it should be written somewhere. And it has these three parts: an entropy term, an energy term, and the energy looks something along the lines of, so you're taking U, a potential, then just to simplify, omega of U is just omega plus the complex hash of U. And then the energy of U is, so you take the sum here, and the integrate on all x, U, omega U to the power J, wedge omega to the power n minus J. If you do this, this gives you an n form, and then an n form times the function gives you an n form. Then you can integrate an n form on x. Okay. And if you sum this all J, this gives you the energy. Maybe this divided by n plus 1, something like that. So it's fairly complicated, and then you have an entropy term, which is just the entropy of taking omega U to the power n. So the entropy is information theory. Okay, so it's a fairly complicated functional. But if you want to show that this functional has critical points, because I remember this is the functional with critical points are exactly solutions for the CSCK equation. So exactly constant scalar curvature matrix. So if you want to study critical points and do some variation analysis, then it's always better to have complete spaces. Okay, so and what do we do? Well, it turns out that there exists a natural metric structure on the set of potentials. It's a Finsler metric structure. I won't tell you too much about it because we don't have a lot of time, but it can give H a structure of Frisch manifold. So remember, H is a set of Kähler potentials. So all the functions with complex hashing plus Kähler form omega gives you another Kähler form. So this is just an open set and smooth function, so it's Frisch manifold. You can define what's the tangent thing, and then you define a Finsler metric and the distance associated to it. It's the distance d. Doesn't really matter here too much, so I won't spend too much time. But the important part is that there's this natural structure, and we can complete it. And this, by definition, is what we call E1. So E1 for us is this completion with respect to this distance of a set of Kähler potentials. Okay, and it turns out that we can extend this the functional with critical points are the constant scalar curvature matrix to the space E1. So this is somehow similar to a geometric version of a L1 space or something like that. Okay, but the good thing is now is that we want to find, so CSCK metrics are exactly the critical points of M, and so we want to find these critical points, and we start well because by this theorem of Berman and Baertsen, and we actually know that this functional is convex with respect to this distance. So when you think of a convex function, you think of something like x squared, and x squared is very nice because it has a critical point. Okay, but there is an issue that not all convex functions are like this, right? So what could happen is that at infinity, you always decrease, but you decrease less and less, right? But so it's not enough to guarantee there exists a minimum, right, for this functional. So you only know that it decreases less and less, but it could always decrease. Okay, so this is exactly the point for this next theorem that I want to tell you about by Chang, that says that M, so this function has a unique critical point, so meaning a unique constant scalar curvature metric if and only if we check that M grows at infinity. So meaning that M is actually equal to something similar to M squared. Sure. Yes.
Can I ask you a question?
Yeah. Please.
So even in the convex sort of asymptotic case you just described, it is always true that if your functional is non-increasing and bounded below, then the derivative must tend to 0. So even if you don't have a point where necessarily the derivative is equal to 0, you still know that along the asymptotic direction, your derivative goes to 0. But that does say something about the Mabuchi energy, right? Knowing that such a limit of the derivative going to 0 exists.
So what you're saying is that if you, in the example that I mentioned, what is happening is that actually it's stagnating. So it's, and in any case, it's bounded.
Yes.
Is that what you're saying?
I'm saying that if you're decreasing, if a functional is decreasing, it's both decreasing and bounded below, then you know that its derivative tends to 0. Which is the best next thing to being equal to 0, as in your x squared example. So the second example is not that bad if you're considering it some sort of time evolution, right? You still know that the derivative tends to 0.
Yes, that's true.
Very small.
Yes. So what you're saying, it's true. So so maybe here's something that I'm not telling you too much, but what's actually happening. So if you're in a situation where the Mabuchi energy it's actually bounded below, then you can find this constant scalar curvature metrics, but this uniqueness it's complicated and has to do with the existence of automorphisms and of holomorphic vector fields. Because of course, if you have an holomorphic, so if you have a 1 parameter subgroup of automorphism, then you can never be unique because you can find these geodesics which are.
I see. So it's in the sort of non-compact convex situation, or sort of non-complete or whatever situation.
Yeah.
The trade-off is uniqueness, but not really existence.
Yeah, something along those lines. Yeah.
Right.
But I mean, it's not true that this M is bounded below.
Well, okay. My understanding is that your stability would somehow guarantee that it's bounded.
No, exactly. Yeah. Yes. So exactly, we'll get there. But yeah, yes.
All right. Cool.
Yeah. Okay. So yeah, thanks for the question. So as I was saying, this Chang result is telling you that M has unique critical point if and only if M grows in infinity. So yeah, I thought I'd take this off. And turns out that this is equivalent to checking that actually for every geodesic, unit speed geodesic, you have, concretely, this means that the limit at infinity of this slope of this function, the Mabuchi functional, along any geodesic, this is positive. Okay. So this is what we'll take, this is at the end of Chang's result, and this is what we'll take as existence and uniqueness of constant scalar curvature metrics. For us, this will mean that for any geodesic in this completion, geodesic ray, then you have unit speed, then you have this limit grows at least linearly. Okay, so this Mabuchi function grows at least linearly. Okay, so all of this was to tell you what we'll take as constant scalar curvature matrix. Now I need to tell you something about K-stability, right? Otherwise, nothing makes sense. Okay, so let's define what's K-stability. So this is not the original definition, and it won't seem very algebraic by this definition, but this is equivalent by these theorems that I mentioned before, Schwarz-Dyrfeld and Dervin-Ross. So we say that X alpha is K-stable if not for every geodesic ray, but just a special class of geodesic rays in the same set that are somehow algebraic, and I'm not telling you what is this right now, but if you want to check that for every algebraic geodesic, whatever that means, you have this positive limit, then we say that X alpha is K-stable. So what I'm telling you is that then to prove the Tian Donaldson conjecture, it's just a matter of checking that if we know that this limit is positive for every algebraic ray, then it's actually positive for every ray. Okay, so maybe if I have time later, I can tell you how these rays are algebraic, but just take K-stability as something that from algebraic data we can come up with array, and the positivity of this Mabuchi function along this ray, it's K-stability. So it's a matter of choosing rays. So the non-Archimedean approach that I mentioned about will be useful exactly to parameterize this set of rays. So these rays will have some non-Archimedean structure, and that's why we use this non-Archimedean technology will be useful. Okay, so up until now, what I said, it was known before, so there's nothing new here. And what I'll start telling you now, it's exactly my contribution. Okay, so the non-Archimedean interpretation of K-stability. I said this is the new part, and this comes a bit of the algebra. Okay. So X, I remember, is our compact Kähler manifold, and I'll define the set IX to be the set of coherent ideal sheaves of X. Okay. So if ideal here just meaning that, so ideal sheaf just meaning that for every open subset of X, we'll give it an ideal of holomorphic functions, and coherent here, it's complicated concept. What you can think of is, for instance, a typical, a nice element inside this set is a set of holomorphic functions that vanish along some manifold. So that's great. And turns out that this set has some algebraic structure, meaning if you take two ideals, you can sum them, and this gives you an ideal. And you can multiply them, and this gives you an ideal. And they're always coherent as well. Okay, so you have sum and multiplication of these ideals. So remember, these are things that are ideals of holomorphic functions. So for every open set, this is an ideal inside the holomorphic functions. Okay. And now define what's evaluation. So evaluation for me will be something that take an ideal and gives you a positive number, possibly plus infinity. And I say it's evaluation if you take the product of two ideals and this gives you the sum. And if you take the sum, this gives you the minimum between the two. So evaluation is just a function that behaves like this. So some dumb, some easy properties that one can assume of a function. Okay, we have defined on a set with this algebraic structure, and maybe here I'll change this. And I'll say that the non-Archimedean version of X will be just the set of all valuations. Okay. So
you're going to
X
give
and
us
A.
an example of evaluation.
Sure. So if you take so if you take hypersurface on your variety on your Kähler manifold, submanifold of codimension 1, then you can just look at the order of vanishing along this this visor. So,
So
what do I
degree.
mean by that? Yes.
So degree. If you're sort of algebraic, would be like some degree, right?
Sure. So what does this do? So if you take a function, then what is happening is that you look at the local equation for E, and you do this around any point. It won't matter if you're E smooth, for instance. Then you just see how many times H divides F, but H to the power K plus 1 does not divide F, and then you say that the order of vanishing is K. And then once you know how to do for functions, you can do for ideals of functions.
Is it not the case that in the algebraic setting where we have polynomials, this is just
no, so okay, so if F is a polynomial, and then you take, let's do, for instance, in P1, and then you take a point. So then the order of vanishing along P of a polynomial F is just the multiplicity of P, so not the degree.
oh, yeah, because it's the minimum, right? You want the minimum, that's fine.
Yeah, yeah.
Okay, cool.
Exactly.
Right, it's a divisibility thing, right? It's not
exactly. It's a divisibility thing.
Yeah,
exactly.
Yeah, that's right. All right, thanks.
Yeah. And moreover, so this is evaluation. So the typical example are these order of vanishings, and this was, yeah, these were called divisorial evaluations, but it's not super important. What's super important though? I mean, these are super important, but what's actually important? Just as a comment. So if you take these hypersurfaces not only on X, but also on birational models of X, then you can always define this order of vanishing. And if you take the set of all such things, then this is actually the set of all valuations is a compactification of all these divisorial evaluations. So the set of evaluation you can give a topology, just pointwise convergence topology, and these things given by hypersurfaces are actually dense. So you can just think as evaluation as something that approximates. Okay, so that was evaluation. Is there any question? So again, evaluation just takes these ideals and transforms in this sense. But then the set of evaluations has a natural class of functions, which are just the most dumb functions you can think of. So if you take an ideal, we'll define a function attached to this ideal, which we'll call log of I. Okay. So this will be the most dumb function you can think of. You take evaluation and you just compute minus v applied to I. It's not very clear why we call this log I right now, but yeah, we can define this. And so log I, let's take evaluation, and applies the relation to I. And then you can take more interesting functions, which is you take a finite number of ideals and then some integers, and then you can cook up a function psi, which is minimum of all these log i's. So you start with the most basic function you can think of, and you just with a few ideals, you can cook up something more interesting. And if you take all the linear span of such functions, we'll call these PL functions. Okay, so piecewise linear functions. This is a lot of notation, but these will all be continuous functions. And yeah, so these in the same way on a complex manifold, smooth functions are nice on X. Now these PL functions will be nice on the non-Archimedean version of X. So these are just functions given by a finite number of ideals and some integers, okay? And why do I care about them? I mean, I was talking about constant scalar curvature metrics, and then I told you all about scalar potentials. How the hell are these two things related, right? So I'll give now a geometric understanding of what are these PL functions. So these functions given by ideals. So let's take one such function, psi. Okay, and let's do the following. So remember that each ij here, it's just an ideal. So ij is an ideal on X. And now if you consider X times P1, this is also a compact Kähler manifold, and I'll call T the variable in P1. And then I'm just saying that if you reorder ij and then sum them if needed, and you multiply them by t to the power kj, blah, blah, blah. So if you do a transformation that has to do with these integers and these ideals, you can cook up an ideal on X times P1. Okay? So I'm just saying that with the data out of a PL function, you can come up with something geometrical on X times P1. And why do I say this is geometrical? Because, well, this is an ideal that has support on X times 0, when we think P1 being C union plus infinity. So 0 is just 0 in C. Because there's this construction in algebraic geometry which is called the blow-up. So any ideal on X times P1, we can actually blow it up. So what does this mean? And then we'll take the normalization. This is just algebraic geometry for non-important things right now. But what is this? So this will be n+1. I mean, it might be singular, but we think of this as n+1 manifold, complex manifold, compact as well, together with a map to X times P1, okay? In such a way that when we look at the pullback of these ideals, so A was an ideal in X times P1, then we have a map that goes to this curly X, which is this blow up. So when you do the pullback of this ideal, it gives you a divisor. So this is something like a sum of abstract sum of hypersurfaces on our complex manifold, if you know what divisor is. But yeah, so the important thing is that out of the information of a PL function, we constructed an ideal, and out of this ideal, we constructed a divisor. And actually, this is a bijection. So, I mean, I'm not explaining exactly what's the red side here, but from a PL function, we created some geometric information on some complex manifold dimension n+1, and this is actually, we can, there's this kind of projection. And why am I telling all of this? Because with this, you can define some non-Archimedean functionals. What do I mean? So you remember that there was this Mabuchi functional, which was the thing whose critical points gave us constant scalar geometrics, and they had a weird, was complicated thing, plus an entropy. Now what I'm saying is that I'm defining a non-Archimedean version of this object, okay? And these, I'll just define it as some intersection numbers, okay? So I'll just explain what's the first term. So again, we started with our function, psi. From psi, we created A. From A, we created a divisor E that lived inside this curly X. And curly X was an n plus one dimensional manifold with a holomorphic map to X times P1, which of course has a map to X, which is just a projection in first coordinate. So we have a map from this curly X to straight X. And straight X, we had this cohomology class alpha, where we had our Kähler form. We can just pull it back to a cohomology class on curly X. And then we can just do this cohomology class and add it E, which is a divisor, so it also defines a cohomology class, second degree. And then we can take top in self-intersection, and this gives us the number. And then you can do some other intersection numbers, and it has to do with these other terms. So this similar to this energy term, and then there will be other terms. I won't super describe this because we're running out of time. Now, in the same way, the smooth functions were the nice functions on X, and I told you that these PL functions are nice on this non-Archimedean version of X. Then, the same way we had potentials here, we'll have potentials here. And what are these? So these are a set of PL functions that has the properties that the divisor associated to them plus alpha is a Kähler class. Okay, so it's a cohomology class that contains a Kähler metric. Then I here say relative because it's relative to the P1, but I won't do too much details, but it's just a matter of a positivity condition. So the functions which are represented by a divisor that once we summed alpha became positive. Okay, and all of this, all these non-Archimedean things, was only to say that then K-stability reads like the following: that for every phi on these non-Archimedean potentials, we have that the non-Archimedean version of the Mabuchi functional is actually positive. Okay, so I remember that before, for us, K-stability was something along that had to do with geodesic rays that were algebraic, and asking that the slope at infinity of this Mabuchi function was positive. And here is also a positivity condition, but it's something that a priori has only to do with non-Archimedean things. Okay, so like in the complex analytic setting, there was a distance on H, and we could complete it. And this became E1. And now what I'm saying is that you can do exactly the same thing in this non-Archimedean setting and get the E1, non-Archimedean version of E1. We can extend the non-Archimedean Mabuchi functional. And K hat stability, which is what I promised in my theorem, reads for every element of non-Archimedean E1, you have positivity of this non-Archimedean Mabuchi functional, which is exactly the same thing as before, but before it was K-stability is only H and A, and here is E1 and A. The whole point is that this thing contains H and A, and it's the completion, but the Mabuchi function is not continuous for this metric. So this is strictly stronger. Okay, and just to finish, how can we conclude how can we get any result like this? It's because it turns out that there's a bijective correspondence between these non-Archimedean functionals and those algebraic rays that I promised you before that were related to constant Kähler Geometry metrics. And in this language, the result of Ross and Soistrom-Dyrfeldt is exactly that the non-Archimedean quantity computes the limit at infinity of this Mabuchi energy. Okay, so there's this correspondence, and so whenever you have a ray, this gives you a function, and actually the non-Archimedean version of the Mabuchi computes this limit. Similarly, one has the same thing for E1, and there's something called maximal rays, which are more general than algebraic. And what I proved in the paper is that although we don't have an equality, we have an inequality. So the non-Archimedean quantity is larger or equal to this limit. Oh, sorry, it's the other way around. Yeah. So that luckily goes in the correct direction. Okay, so to finish off, I just say that.
Sorry, are you sure that was quite right? I think the result you had before guaranteed that the limit was positive. And so if your sign was the other way around, then you would control the Mabuchi energy from below, which would be a very good thing. But in this direction, I'm a little perplexed.
No, because we want to suppose that this is positive.
Ah, okay. You want to start from, okay, you want to assume that it's bounded below from the outset.
Exactly, because K stability would be exactly this positivity,
yes,
but for phi on H and A. And here, what I'm supposing in my theorem is that M and A of phi is positive for every phi in E1. So it's
all right. So hat stable is going to imply that they're bounded below, and then you conclude about the limit of your rate of variation of Mabuchi energy from the above inequality. I understand now. Thanks.
Yeah, that's exactly it.
Yeah,
so that's exactly it. So how do we finish the theorem? So we want to K hat stability imply the existence of metrics. We prove by contradiction. If there isn't a constant scalar geometric, then by Chen criterion, M is not coercive, so M does not grow, meaning that there exists an array whose slope at infinity is negative. But then by the result of Chile that I mentioned before, we get that UT is maximal, meaning this ray is one of the rays we can compare with algebraic geometry. And with with the slope formula that I told you before, we get that since this is maximal, it has defined something non-Archimedean, and with this something non-Archimedean, the slope formula that gave us this inequality, this one's in E1 and A, and by K hat stability, this was positive. And this completes the proof. Thank you very much.
All right, thank you. So people can clap with their hands or with the clapping button here, which is convenient. I think we have time for a short question, if people may. Are there any questions for Pietro? I know I asked quite a few questions during the talk, so it's kind of good. But are there any? Pietro, maybe just a quick question.
Yeah.
Can you show me a K-hat stable set of data to begin with?
Yes. So
check.
What?
It doesn't seem very easy to check.
No, it isn't. So what I didn't tell you about, which was in the title of the talk, is what's the non-Archimedean approach to prove the Donaldson conjecture. So we know that CSCK implies K stable, and we know that K hat stable implies CSCK. So the non-Archimedean approach would be to prove that these two things are equivalent, since they're both said in non-Archimedean terms. So conjecturally, the check K stability is just as hard as checking K bar stability, K hat stability. But of course, in practice, it is more complicated. People check K stability, which is also something hard to check in low dimension for Fano manifolds. And there's a evaluative criterion, which is very important, and it's something that I'm trying to work on this K hat stability. Yeah, as you said, it's of course complicated thing to check.
So
Yeah.
do you still have to work over test configurations and rest of it? Is it the same mindset? You don't have to give me the details. You just want to.
Sure. So if you know about test configurations, then K stability is just checking that this Donaldson Futaki of test configuration is positive.
Yeah.
And this Donaldson Futaki is just the same thing as just a version of this non-Archimedean Mabuchi function, as I said. Okay, and this K hat stability, it's exactly the same thing, but instead of checking for every test configuration where you ask that L is relatively Kähler, so you just drop this assumption for L big. So checking K stability is just checking that this Donaldson Futaki invariant is positive on big test configurations instead of Kähler test configurations.
Oh, I see. So you weaken the positivity to just merely big.
Yes, meaning that one needs to check in a larger test set. And it's somehow the same thing as saying that you need to check on this E1 and A.
Cool. That's cool. All right, I understand. Thank you. All right, if there are no further questions, can we thank Pietro again, please? You can do this either by clicking or by clapping. Depends on your worldview. Cool.
Well, thank you very much.
All right, Pietro, thank you so much. This was lots of fun. Everyone, feel welcome to show up in 2 weeks' time and check our calendar at the link. The calendar is updated, so let's see what